Okay, good morning, everyone. Thanks again for the invitation of the organizing committee, and I will talk about the investigation of possible features for the classification of signal and background with CNN in PandaX-III. Here's our outline. Firstly, I will introduce briefly the neutrinoless double beta decay and the PandaX-III experiment. Secondly, the data preparation, and then the signal and the background classification with CNN, and then the features of the network and the physical explanations, and at last, the summary. So, neutrinoless double beta decay is one of the hardest issues in particle physics. We will verify that neutrinos are Majorana particles, and will also show us the lepton violation beyond the standard model. Compared with the two neutrino double beta decay, if the neutrinos are their own antiparticles, the neutrinoless double beta decay could happen, as no energy is taken away by neutrinos. The energy of the two electrons is a constant. In the experiment, we measure the sum of the energies of the two electrons. Neutrinoless double beta decay. We have discovered the two neutrino double beta decay for 11 isotopes. As you can see in the picture, here we are using xenon-136. This is the isotope to its high abundance in natural xenon and the relatively low cost of enrichment. And as a calorimeter, PandaX-III measures the energy of two electrons from neutrinoless double beta decay and constructs an energy spectrum at the region of interest around the Q value of xenon, which is almost 2.5 MeV. In practice, PandaX-III collaboration is building a 140 kilogram level detector to search for neutrinoless double beta decay of xenon-136. As shown here, the detector is a TPC of single N, the readout plane on the upper side, and the cathode on the bottom. The drift distance is 1,200 millimeter. The diameter of the readout plane is 1,600 millimeter. We will use 52 microbulk micromegas as the charge readout plane, with two series of strips of 3 millimeter pitch. The working gas is 10 bar xenon. The TPC can record both the energy depositions and the three-dimensional track of an event. As shown in this figure, this is a projection of the track in XZ and YZ plane of a neutrinoless double beta decay event from our simulation. The track is at 20 centimeter level. It could be used to distinguish the signal and the background events, for example, by using the blobs here. Yet there are several ways to distinguish signal and background events. Here, we're using machine learning to do so. So now let's step into CNN in PandaX-III. Before starting directly our machine learning process, we need to generate our dataset. We use the REST-G4, which is a framework that's dedicated to the generation of data, with PandaX-III TPC geometry, which you have seen before. We simulated our data, and the diffusion effects and the electronics responses are utilized in the simulation. Since thorium-232 and uranium-238 are both the major background which contribute significantly to the background in the region of interest, we simulated in total 320,000 neutrinoless double beta decay events and 320,000 background events. Here you can see, after an event has gone through a series of processes, as shown in the figure, original event to the final result, the track becomes more blurred and a lot of information is lost, but this is more in line with the actual situation. The raw data is not convenient for machine learning, so next we need to prepare our data which could be nicely fed to our machine learning model. As the readout plane is based on XY strips, so the detector could record only the track projection in XZ and YZ plane. So for our data, you could see from this GIF that we transformed a three-dimensional event into a two-dimensional picture by combining the projections in both XZ and YZ plane. We also calculate the energy center and make it the center of our picture to make sure the position of two tracks are in line. We use R channel for indicating XZ plane and the G channel for YZ plane. The intensity of the color represents the amount of energy, and our figure is set to 64, multiply 64 with 3 mm beam. As you can see here, the window is big enough for neutrino-less double beta decay event. We also divided the data into 3 parts, that's 7 to 1. Also, in order to make our model more robust, we adopted a series of data augmentation like random sharing, rotation, and horizontal and vertical flipping. So up to now, we are ready to construct our model. Before choosing our benchmark model, we need to compare the results of different models that are not optimized. As shown in the figure, epsilon s means signal, which is the path rate of neutrino-less double beta decay. So epsilon b is background recognition rate. Since the performance of the instrument is determined by epsilon s, divide root epsilon b, as you can see the formulation here. So we define it as significance. We can see clearly that EfficientNet performs best, so we decide to use EfficientNet as our benchmark model. It is not difficult to see from this structure. It refers to the residual of ResNet. The concept also uses a module called squeeze and excitation to determine the importance of each feature channel through independent learning. In this way, we can promote useful features and suppress less useful features. Finally, the baseline model we chose is B4. You can see from this picture, which is from Google, that there is a great accuracy improvement on the basis of B3. And for B5, it almost doubles the flops, but only obtain a small accuracy improvement. So after the selection of network, we altered the configuration and changed the hyperparameters in order to get better result. You can see the hyperparameters we listed here. The result is impressive. We achieved the 93.5% accuracy on the training set, 0.45% on the validation set, and 92.70% on the test set. You can see from this picture that there was no serious overfitting. The table here is some important indicators, the most important of which is the optimal value of significance, which is 190.6% higher than CDR, 6% higher than our previous work. Now we are prepared for the feature study, and that is the key point of this talk. Let's look at the first layer. We can find that all filters can be divided into different types, though the two channels are divided into only responding to XZ plane, as you can see here in the picture, and only responding to YZ plane, or responding to both of them. We have also filters that detect the edges and the filters that respond to energy points. It is worth mentioning that these features have nothing to do with this specific picture. That is to say, for different pictures, the function of these filters are consistent. For the middle layer, we found a large number of feature maps outputting 4 points. Through comparison, we can find that these 4 points correspond to the 4 Bragg peaks of the event. There are also some filters that still detect the edges of the event. And for other filters, we believe it is also an attempt to detect the Bragg peak, just the detection field. This can be seen from the comparison of the activation maps of different events. As you can see here, the differences. For different events, some filters successfully found the position of the Bragg peak while others failed. And for the last layer, we first analyzed the parameters of the fully connected layer that followed, as shown in the figure. After normalization, there are in total 7 dominant filters, 3 positive 1 and 4 negative 1. So we are curious whether the output of these 7 filters is related to the type of model prediction. As shown in the figure, we can see that the feature map and the predicted value of these 7 neurons are closely related. From 0 to 1, the maximum value of positive neuron is getting larger and larger, and the maximum value of negative neurons is getting smaller and smaller. At the same time, we call the 2 filters on the left here supplementary filters. Let's finish looking the changes of 7 filters with predicted value from 0 to 1. You can see the changes here. The maximum value is getting larger and larger for positive neurons. Okay. Let's now focus on patterns for neutrino-less double beta decay-like events. As you can see in the picture on the left, we want to emphasize that if the predicted value is close to 1, it means the model tends to classify this event as a signal event. In contrast, if the predicted value is close to 0, the model tends to classify this event as a background event. There are some features about these 7 filters we found. For example, the position for maximum positive filters is fixed, and the absolute value of maximum of negative filters are neglectable. Also, the 2 supplementary filters here compensate for each other, as well as the other unimportant filters, and their maximum values are much lower than those of positive filters. Here are some examples. You can see they are very similar. And then for the middle predicted value, which refers to uncertain events, the maximum position are no longer fixed for both positive and the negative filters. The absolute value of maximum of positive and the negative filters are comparable, and the 2 supplementary filters show little difference from the other filters. Here are also some examples. At last, the background-like events. However, the maximum position for negative filters are not fixed, but the absolute value of maximum of positive filters are neglectable, and the 2 supplementary filters compensate for each other as well as the rest of unimportant filters again, and their maximum values are much lower than those of negative filters. Here are also some examples of background-like events. So, to make it more clear, we analyzed these 7 neurons by manually calculating the predicted value, considering only these 7 neurons. Then we draw the distribution diagram of the arrow. We can find that if only these 7 filters are considered, the predicted value is almost the same as the predicted value with all filters. The largest arrow here you can see is 0.06, and most of them are less than 0.02. Secondly, considering only 3 positive filters, there are 2 peaks on the arrow distribution map, one near 0 and one near 0.5. If we subdivide further, we will find that for the neutrino-less double beta decay event, the predicted value is almost the same as the true predicted value of the model with all filters. This is also true for 4 negative filters, which show extremely high accuracy. So we can say 3 positive filters are effective for distinguish neutrino-less double beta decay events, and the 4 negative filters are effective for background events. And you can see from this table that the 7 filters contribute most to the classification as the significance value is comparable with our best result. We can't help but wonder why it only takes 3 neurons to predict the neutrino-less double beta decay event and only 4 neurons to predict the background event. Is it because a neutrino-less double beta decay event only requires a maximum of 3 parameters and the thorium-232 or uranium-238 decay only requires a maximum of 4 parameters. We have not conducted research due to the time constraint, but this is the direction of our future work. Finally, here comes our summary. The trajectories of particles in PandaX-III play an important role in the classification of signal and background. Using efficient net, we obtained a much better machine learning result comparing with our previous work, focusing on the study of features. First, the several layers extract the superficial features, while the 7 filters in the last layer indicate abstract features and contribute most to the classification of signal and background. And for our future work, we can try to modify the structure of the existing network, or we can change the rectified linear activation function ReLU to ELU or switch, etc. We may also be able to connect 2 networks of different structures in parallel and reconnect their fully connected layers together and output our predicted value. And that's all of our talk today. Thank you for listening.
Thank you very much. So we have some questions that we'd like to ask. So those questions I will just read off from the from Slido. Let's see. While I'm trying to share it, maybe the first one I'll just ask is, could you comment on how you optimize the hyperparameters?
Okay, yes. So could you please turn to page 9, I think.
Okay.
So as we can see that we only conducted some simple configuration of the hyperparameters. First is the input resolution. We choose it to be double the just 128 by 128. That is because our original resolution is 64 by 64. So if we make it into 128 by 128, then 1 pixel is corresponding for 4 pixels, and without any changes of the raw information. And then we think maybe there will be useful for the model to learn some more detailed information. And the next is the number of filters, and that is we did a lot of work on, and that is because unlike traditional image classification task, our task is to classify the physical reactions, which does not have so many features for us to choose. And in this case, we only have two types of events. One is neutral-less double beta decay, and the other is background event. So we think maybe the number of features that the model used to predict the value is affected by the filters of last convolution layer. So we change it. And can you turn to page?
Okay.
Let's see. 22. Yes. Sorry, page 22. And this is what we obtained after we changed the number of filters of different of the last convolution layer. And we can see that the configuration with 64 filters performs the best. And so we chose that. And then next, can you turn back? So next is the max pooling. That is because we read about some papers, and it suggests that the max pooling is useful for learning the information of the edges, which we think is more appropriate for our model. So we chose that. And then the learning rate and the optimizer is just we did a number of we try a number of times, and then it performs the best.
Thank you. I think that's great. Maybe you have time for one more question. The highest voted one is the following. instead of projecting onto the X, Z, and Y, Z planes, could you use PCA to project onto the feature axis, which retain the most information?
Well, okay. This is a good question, but so firstly is this is what our detector directly detected. This is just the raw information from the detector. So we want to keep that, and because after the simulation of the REST framework, we will use our data. We will use the data collected by our real detector. So we want to keep that the same. And then the second is, if we use PCA, maybe it will vary from one single event to another. So perhaps we don't have a unified or we don't have the same the axis for different events. Yes.
Okay, thank you. Maybe I try to squeeze one more question since it's up for it. Thank you very much. That was a good answer. So the question from Micah, maybe, what else besides neutron-less double beta decay is included in the signal-like, so neutron-less double beta decay-like category? Are there any detectable differences in response between the signal, neutron-less double beta decay, and say single Compton scatter or something?
Well, first we use the energy range to separate them, to distinguish them. I believe the range we chose in the REST framework is from I don't remember the exact word, maybe from 2,415 electron volts to something close, and we only take this energy range to into the simulation part, and then there's only two types of decay which also has this same energy range. That is the thorium 200 and 32 and uranium 238. So this is the three type of decay we want to distinguish. And the last two, we classify it as background events.
Okay, thank you very much. Thank you for these three answers, and also the nice talk. Thank you very much.